where we can look at another concept learned in engineering. The first one was all about acceleration versus time and velocity. And so in example 2, let's look a little bit into circuits. Some of y'all have done circuits in high school before. It's just fantastic. And some of y'all that probably, at least, I mean, going into engineering, y'all have probably all heard some of these concepts before. So let's get these back into our brains just a little bit. You know, this drawing over here on the left is just a basic circuit board. You have V of S, which represents a voltage source, and I always represent your current. And current flows in a diagram from here always flows from the positive to the negative. And so it's going from this positive right here on top, and it's flowing around towards the negative. And that's just in general how current flows. The R stands right here is for resistance. Okay, so a basic symbol that's connecting, or a basic equation that's kind of connecting these three variables together is what's Ohm's law right here. And Ohm's law says that the voltage is equal to I times R. Okay, so voltage is your current times your resistance. And a lot of times what I do is I kind of rewrite it a little bit to, this is how I more understand it, is I treat it as I is equal to V over R. So the current is almost a relationship between the voltage and the resistance. The current is always measured in amps, voltage is in volts, and the resistance in terms of ohms. And some things you can think about is, like, if we think about our house, okay, what the city does is applies us an even amount of volts. And so this top part of this fraction always stays constant. It's always what's provided to us. Okay? And then, so we've got this current flowing through our house based on our voltage, and depending on how much we use of it, how much resistance we apply to the system is really how much current's flowing. The more higher our resistance, the less current that's flowing in our house, and kind of vice versa. If you think about those times when, you know, if people that go over to Europe and they always say, oh, I have to bring those converters, whenever they have like a hair dryer or a like say a flat iron or something, and they want to go over there, and they, in order to actually use their product, they have to put a little converter on, they have to plug into a converter, and then they can plug it into the wall socket. Well, that's just because what's over in Europe is a higher voltage source. And if I went in there right away and I plugged in my curling iron as is, I'm going to fry it because it's providing too much current than what my actual hairdryer can hold. And so what we're going to do is, in order to keep the current equal to what it can handle, is we put this little converter on there that increases the resistance because the voltage is higher. Okay, so by increasing the resistance, that'll keep I constant to what it's used to being able to do, and we don't fry our whatever we've brought over to try to use. And that's what's kind of going over there in Europe. And you know, sometimes when it gets like in the middle of summer and it's super, super, super hot, in big places like Dallas, they have to do random blackouts. It's because what's going on there is, to their system, it's just that there is, of the total amount of voltage that's provided, there's too much current being there, or the current's dropping because there's too much resistance being pulled on the system. So this R is getting so large that there's so much people trying to draw on it with their air conditioning units and everything else, that the current is getting too low, and to save from, like, if you want to call it crashing the system, then what they have to do is do random blackouts to keep everything in balance. So that's kind of, hopefully, a little more idea. You're kind of getting an idea of really what's going on here with circuits. So let's kind of go on. Let's talk about a little bit more. And so Ohm's law is very, very important. Another law is Kirchhoff's voltage law, KVL. And what that guy says is the whole sum of the voltage rises is going to be the sum of the voltage drops. Okay, so Vs is equal to VR plus V. And we know what VR is just by Ohm's law. VR is our current times our resistance. So total, this is kind of the equation we're going to focus on. So Vs is equal to I times R plus V. And like before in our acceleration diagram we just did a second ago, what it was doing was relating our velocity to time. But what this one does here is it's relating your voltage to current. Okay, it's relating this voltage right here to our current I. And since what's being related is voltage to current, then what you're going to see is the voltage, V of S, is our dependent variable, which sometimes we see is that's the Y, and then our I is going to be the independent variable, which sometimes we see as X. Okay, so moving on to what the problem's going to ask us kind of do so we can get some practice here, is we want to find the values of R and V if the values of the voltage and the current are known in the following 2 points. Okay, so there's our our dependent variable, and here's our independent variable. So I is what's being graphed on the x-axis, and voltage is what's being graphed on the y-axis. Okay, and if we've been given a table of values. When we have 0.1 amps of flow, then the voltage source is required is 10. When we have 1.1 amps of flow, then we have 20 volts. Okay, so kind of this T-chart's a little bit backwards, and that's what you need to pay attention to, in the sense of here's all of our X values right there, and then there's all of our Y's. Okay, well, let's get started just kind of like we did in our last example. First thing we want to do is, if we want to write our equation, we're used to seeing y equals mx plus b. Well, and how that's going to relate over here is instead is Vs is equal to, in this case I'm going to go ahead and do my slope value, which is now R, because I is our X, and then plus our initial voltage. Okay, so here's my y equals mx plus b. So let's find our m. So m in this case is R. Okay, and it's going to be the difference in my y values, so the difference in my voltage over the difference in my current. So let me come back up here for 2 seconds. The difference in my voltage, so 10 minus 20, over the difference in my current. So 0.1 minus 1.1. And when I plug this into an equation, I'm going to get my R value to be 10. And 10, because R is in resistance, it's going to be 10 ohms. Or if you didn't want to write the word ohms, you can say R is equal to 10, and then here's your symbol for ohms. Okay, so let me come over here and let's start building our equation. So right now we have our equation as Vs is equal to our R, so 10 times I plus V. So all we have left to do is find our initial voltage, and then we can kind of have a full equation, a full equation. So let's keep working just like we did before. All I have to do is pick one of my 2 points. So let me pick like that 10 in the 0.1. And let's plug this into our main equation. And you know what? I think I wrote it backwards. Let's go back to that one more second. Yeah, because the 0.1 is our x and the 10 is the y. So let's scratch that for a second. So 0.1 comma 10. Okay. And plugging that into our equation, then we'll get 10 is equal to 10 times 0.1 plus V. And solving that out for V, by the time we get all this together, then we'll get that to be 9. We can call that volts. Alright, so all together into one main equation, then Vs is equal to 10I plus 9. Box that up, and that's an equation to represent the information that was given to us. And in the problem, they also, we can either write the equation or we can circle this part too. So they want to know the resistance for those values, and we also want to know the volts for those values. Okay, and then if we kind of go back up to our graph so we can put this all together, we had, let's see, at 0.1 amps, so very small, we're up at 10. Okay, and at 1.1 we're up at 20. So 5, 10, 15, and 20. And our initial voltage was that last thing we found, which was 9, which makes sense. It's fitting right in there. So if we connect all the dots, you will see your linear equation just right there. Okay, now I kind of told you guys before when we were first talking about this that sometimes you can treat, instead of letting like V, the voltage being your independent or your dependent variable and letting current, which is I, being your independent variable, you can sometimes swap it around, where now in this case, instead, you can let your voltage source, Vs, be your independent variable, which sometimes to me it kind of makes a little bit more sense having your voltage be your independent, just because that's what's kind of given. It doesn't really change because that's what's provided, especially in households. And so in that case, your equation would look something more like I is equal to, you would solve it for I, it'd be 1 over R times your voltage source minus V over R. Okay, and that's just a kind of taking our main equation, just rearranging it. That's all I did right there. Okay, and then if we did that, then the same way, and took that and did all the math that we just did above, where we picked the 2 points and found your slope. Okay, in that case, your slope, which is represented, let me write it like this, it would be more of like y equals mx plus b. Then this ratio right here is b. 1 over r is actually your slope. Okay, so if we go through, though, and we still do the slope in the sense of it's going to be the difference in the i's, so I1 minus I2 over the difference in the velocities, so V1 minus V2, you get your slope to be 0.1. And then when you go back and find a V value using one of those exact points, then you get a B value to be negative 0.9. And so in that case, then your overall equation is going to be I is equal to 0.1 times your voltage source minus 0.9. So that's just another way to look at it if you decided to switch the variables around and make your voltage independent and make your current the dependent variable, which kind of makes sense to me. Like I said, your current, the amount of current flowing through your system depends on your voltage source. So it's just another way to look at things. But let's go on to our next topic.